Starting back in 2012, most of you are familiar with HEC 18, HDS 7, and other manuals. That was really officially the first year when we started officially recommending or providing guidelines for the use of two-dimensional modeling for complex bridges. Now, we put that out there in 2012, recognizing since then there's been a lot of hurdles for states to accommodate that and start doing that. And quite honestly, in the federal highway side, we've been working to help states get there. And most recently, starting back in 2017, there's a program that Federal Highways has called Everyday Counts. And you can see the title up here. And we have an innovation in that program called Change. See at the top, collaborative hydraulics advancing to the next generation of engineering. And that's what it's about. It's trying to help states advance in using 2D modeling for complex bridges. We've had resources to help with training, develop reference documents, several other things. I'll be speaking about scour tomorrow and where we're going with that. But one of the elements is floodplain and floodway analysis. That's a very important component, and quite honestly, it's a barrier as we try to transition from 1D to 2D modeling. Aquaveo has been working with us to develop new tools to assess floodplain impacts as well as to delineate floodways. So Alan has a lot of great stuff to share. I won't take any more time, and I'll pass it on. Hopefully, I think this will generate some good discussion, so I'm eager to hear what you have to say.
Thank you, Scott. Is this working? Not enough, or do I need to use the other microphone? Can you hear me? I can't get it much closer to my mic. Is that okay?
Keep going. Keep talking.
Okay. Hey, great. Scott took 2 minutes without even having a slide, so it's a good thing he gave the time over to me. I'd like to thank Rachel for her presentation. It illustrates nicely the problem that we're trying to address. The floodway has been developed for a concept of a 1D model, and as you start integrating that into a 2D world, which, as Scott indicated, is the direction we'd like to see hydraulics and hydrology going, it raises a lot of questions, and my presentation today will show us some tools that we've been working on as part of EDC and hopefully start stimulating some of the discussions that need to take place. We'll look at a case study that we're using. We've actually applied some of these tools to a half a dozen different locations, but we'll look at a case study of the South Platte River in Colorado, and we give thanks to Colorado DOT and others for their contributions on some of the data that's come in here. I'm not getting updates here on my slides, but I'll try and watch from what's over there. Let me go back one. We'll actually talk about two different things. We'll talk about floodplain tools that are available now in 2 dimensions, and similar features are available for several models. Rachel showed a slide with the floodway or the floodplain coming out of RASMapper, and we'll look at some of the questions that come up that way and other floodplain issues, and then hopefully I'll spend the bulk of my time on the floodway question. If we're talking about floodplains, traditionally in 2D models, the floodplain is a discrete thing. That means you build a mesh or a grid, and whatever cells stay wet are the floodplain. The problem with that is that's a discrete wetting and drying step. As a cell is either wet or dry, so if your cell is 50 feet across, you have a jump of 50 feet when that cell dries out. The solution to that is interpolation. Now, interpolation is a necessary evil in our world of numerics. We don't necessarily know the details of what's happening in interpolation, but we use it. So the tools that have been identified and exist in both SMS and in RASMapper allow you to take the elevations, the water surface elevations computed by the model, and interpolate those back to high-resolution rasters or LiDAR sets to determine what to map the depths. So if we look at this image of the South Platte, and zoom in on a region, this shows the depth based on individual cells that the computation was performed on. And notice there's fairly consistent depths. The green colors show shallow depths, red colors, or blue even more shallow, just barely wet, and the red is the channel. If we map that back to the original resolution, the high resolution LiDAR raster data, you now start seeing individual channel cells, braided streams, and other depths. And by mapping that, we also aren't limited to the resolution of the mesh. This gives us a much more complete picture of what the depths are, but it also can lead to questions like Rachel showed, where you actually have puddles of depth that may not be easily defined or described or explained. But that's one tool that's available to us to get a better understanding of what the floodplain is from a 2D model. Now, another tool that we've been developing started out with a description of a fast floodplain modeler, and it is specifically allows you to get a what-if scenarios when looking at the floodplain. That allows you to bring in the FEMA flood hazard maps and put them on display, and using whatever elevation data and base flood elevation data is available, you can delineate what the floodplain would be just doing digital mapping, and then quickly say, well, what happens if we raise the floodplain, raise the base flood elevations by a foot? So in this picture, you see the red line is a digital map of the floodplain on top of the FEMA map, and then if we raise it by a specified amount, in this case it was 1 foot, you'd see the impact in different areas. So those tools are available for evaluating floodplains. As I said, I want to spend most of my time talking about floodways, and we'll use this case study of the South Platte River. It's a very sinuous channel. It has a bridge crossing with 13 wall piers. We looked at the 100-year flow rate and a 3-mile stretch of river. And the picture there shows the 2D results of the floodplain. The problem with this initially is that it's not a single flow channel. There's actually 3 different flow paths. There's a breach of the highway on the south end, in addition to the main flow channel, and another breach just south of the bridge. So if we try to look at this from a floodway definition, this is a slide or picture from the FEMA documentation trying to define what a floodway is, where we're conserving a corridor adjacent to the channel to convey the floodwaters of the 100-year flood without raising the water more than 1 foot in a general scenario, or less if a higher restriction is imposed. So we wanted to look at how we could try to represent this in a 2D world. A couple of proposals have been made in the past, and we built on some of those. The 3 methods that we defined were a cross-section based method, trying to stay true to the HEC-RAS approach. The second method was a unit flow rate threshold method, and the third is a percentage of a Q100 footprint. And I'll describe each of those 3 and hopefully bring up several discussion topics. The cross-section method expands from what the 1D model does, but takes advantage of the velocity profile that is computed by a 2D model. So if we look at a typical cross-section, we might see something like we see here on the bottom. The top is the velocity distribution computed by the 2-dimensional model. And that's different from what we're used to in our 1D model, because 1D will have a velocity that we get in each floodplain and a velocity in the channel, and it's assumed to be constant. And here we see a much more varied velocity distribution. The approach just pulls an equal amount of Q from each side and iteratively computes how much flow we need to put into the center to compute the contractions for a floodway using a 2-dimensional velocity distribution. And so the approach that we take for a simulation like this South Platte River is take the cross sections that the user supplies. You also have a center line and bank arcs, or they're optional. You can enforce bank arcs to prevent the floodway from infringing on the channel itself. And then our tool internally interpolates a user-specified number of cross-sections, so we have a large number of cross-sections, and we apply that encroachment procedure that I described in the previous slide to define a left and right encroachments for each cross-section. And you can see in the picture there, the black line that's going up and down the floodplain is actually just connecting dot to dot the encroachment limits for each cross-section. So then our approach says, well, that black dot becomes our candidate floodway, or that black connect the dots image. We smooth it out, and we create a new mapping of the materials for the two-dimensional model. Anything outside of this floodway just gets turned off. And then we can rerun that through the 2D model, providing a new boundary condition downstream with the raised water surface elevation, and it gives us new water surface elevations. And if we compare that to the original floodplain water surface elevations, we can generate very easily an impact map of the floodway, where in this case, the transition from blue to pink is transitioning to above our 1 foot limit. So we look at that and say, there's we had a target for 1 foot rise. Everywhere that's blue is 1 foot. Getting down into the greens is less than 1 foot, and the pink or magenta colors there are violating our 1 foot limit in individual spots. This is the first discussion topic is, what kind of tolerance are we going to have in a 2D model for a 1 foot rise? Is it every point has to be below 1 foot? Or is it average across the cross section or average across the floodway? That has to be answered. And I have opinions, but I won't try to prejudice anybody from there. The second approach is to use a unit flow threshold. This is an approach that was documented by the two-flow developers in a paper a few years ago, where you take your model and you create a unit flow data set, which is basically just multiplying the depth by the velocity and picking a threshold value. In this case, we picked a value of about 9 feet per second squared and define a zone that exceeds that 9 feet per second. Now, this makes it look like it's a very discrete on and off type situation, but it's not. The holes in the middle there aren't 9 feet per second squared, but they may be very close. So our floodway has to contain something like this. The approach presented by WBM and the two-flow developers proposed a managed floodway or a floodplain where regions inside this zone could be used for development. What we tried to do is try to be more true to the floodway concept. So we smoothed that area out, delete the puddles and ponds, and just create a new floodway corridor approach. And then we did the exact same thing we did with the 1D approach, generate a new map, apply the floods, and look at the water surface elevation changes. And again, we have a few spots individually that exceed the 1 foot limit, but by adjusting that Q threshold, we can get to somewhere that looks fairly close. And that was just the sample that we pulled for this one. Now, the third approach says, well, why don't we look at what's naturally there? Let's take the Q100 or some percentage of the Q100 and see what gets naturally wet. Those wet areas should be the logical locations for a floodway. And so we iterate on the percentage of the Q100, and in this case, we started about 60% and found that we weren't getting near enough constriction, so we ended up dropping all the way down to 30% of the Q100, and that generated a polygon similar to what we had with the unit flow rate. We smoothed that out, mask it, generate a new 2D flow result, and look at the results. Now this actually created a different observation for us. The purple areas on the upper right side and down at the inflow boundary are actually decreases in water surface elevation. The 1D assumption says that any decrease in the water surface elevation must be drawing us towards critical depth, and that's bad, so that can't happen. It's not allowable in a floodway. In this case, the velocities are actually going down and the water surface elevation is going down because we're accounting for all of the 2D flow paths. And the floodplain in this case, or the floodway, has cut off an entire flow path. So a lot less flow is going through that area in the upper right side. So how do we answer that question? I'm not sure. The result then is we've got 3 different tools that are outlined in a tutorial and sample workflows for working with any 2-dimensional model result. These tools apply not just to the SRH2D tools that Federal Highways has been promoting, but also to 2Flow or RAS2D results or ADH results from the Army model or any of the other models you may have access to. But we've got 3 different candidates for floodways here. And if we look at them side by side, they each have different areas where they're coming closer. The engineer can still go back in and adjust the floodway proposal and reapply a piece of the tool to see what that floodway proposal does to the affected water surface elevations. And there needs to be a lot of discussion on that. Now, just as a side note, when we're saying how strictly should we judge this 2D model, we said, well, what happens if we compare this to the 1D floodway that RAS computed for us? Well, here's the 1D floodway. And we did the exact same thing, used that as a map and masked out the area. On the left side, you see the 1D results from RAS telling us that we'd expect between a 0.84 and a 1 foot rise on those cross sections. The right side shows the 2D model results that the water level increase is really more bit like 1.5 to 2 feet everywhere in the floodway of the 1D model, which says, okay, I don't know what we say about that. The 1D model is assuming totally effective conveyance downstream for every cross section. Maybe this is telling us we've been kidding ourselves a little bit. Anyway, lots of discussions. Uh-huh. You mean in running the 2D model?
Yeah, in comparing the time approach model to
The computation times, because you've already got the analysis done and you have an initial water surface, we can set up an initial surface that gives you don't have to worry about spin up times, but it's still, I mean, in these we were looking at 1 to 2 minutes per run to get an analysis done. This one had about 40,000 cells in it, so it was fairly high resolution. I mean, it's not 1 million cells, but we don't recommend that you use 1 million cells. Yeah, Dave.
I'm just curious if instead of the example where it's a little bit lower than 1 foot, we averaged it, so we had some higher, some lower within one section, would that floodway then be less in the 2D and more matched to 1D?
We were looking at with the one-dimensional methodology. We had the 3 methods. The one-dimensional methodology tries to match closely the 1D approach. And we pushed it just so that we were pushing the 1 foot limit somewhere on a cross section. The average, if we averaged it across the cross section, we were still at about a 0.8 foot rise at worst in that method. So you could push it down some. It would come closer to what the HEC-RAS model does, but the HEC-RAS model had entire cross sections that were above 1.5 foot to 2 foot rise when you just did a 2D analysis of the 1D floodway. So it gets closer and it does a similar thing, but it just gives us some information that I wanted to bring up for discussion.
Going forward with FEMA, that's going to be an important question that needs to be answered.
Yes. What should that answer be? Are we going to average across the cross section? Are we going to average across the floodway? Or are we going to hold a 2D model to a standard that it has to be less than 1 foot anywhere, not just at cross sections and not just at an average of a cross section? And I brought that last slide up just to illustrate if we're going to hold the 2D model to that kind of standard, maybe we should hold the 1D model to the same standard.
So Dave, let me comment on that. One thing Alan didn't say in the presentation is that all of these tools will be released soon with the SMS package 13 in the community version, and it will be beta, but we need input. We need you to kick the tires. We need response from your floodplain administrators. Quite honestly, I've been going to the national floodplain conferences and we're kind of spinning our wheels. We need to put this out there. We plan to write a white paper and put some thoughts out there, but we need response how can we help implement this and get this accepted with floodplain administrators? It's not going to be decided at FEMA. It's got to hit the ground. So we definitely need some kick in the tires, and we need input and feedback. So, any other questions?
With the third scenario, Alan, in that comparison, 1 foot rise in the 2D, would that would still be cross-section based with a floodway?
We could still do a cross-section based 1 foot rise. We can easily compute the average rise across the cross-section. The question we had is if we go to a full 2D world, you won't have cross-sections.
Right, well, I mean, it seems like that would be simpler for everybody
Yeah.
in the future.
Yeah, our tools have all been based on let's average back to a 1D approach because that's what the floodplain managers are used to seeing. And so the initial results show that we can actually get a better automated definition of a 1D flood or a floodway that will have a near 1 foot rise everywhere by using a cross-section based approach, but we don't want to totally be dependent on cross-sections.
I think you touched on it, but I was just wondering what the FEMA response is, or is it like a collaboration with FEMA, or are they taking sort of a wait and see?
We need to remember that FEMA doesn't have their own technical people. And they'll look to people like the Federal Highways and the Army Corps to say, well, you tell us what models are acceptable and how this is done. And they look to the floodplain managers. That's where the pressure is on the floodplain managers. So that's why Scott says we need to get feedback from you. And as you're working with your floodplain managers, your experience with North Carolina floodplain, how would they react to this? Because this is more information than they've ever had. It may mean that they're getting bigger floodways, which means they're going to have a lot of press pushback from the communities. It may mean that, yeah, we've got another relief like the case that Teresa showed, that Rachel showed, that, yeah, there isn't a floodway here. The floodway is much smaller than it really should be.
But to help answer that question, this is new ground. There's no other floodway delineation tool in a 2D model out there. FEMA's been kind of quiet on the subject. There's been a lot, again, wheels spinning at conferences. You can take a 2D model and enforce, like Alan did, enforce the 1D corridor. That's been done. But so this new ground as far as tools. There's some decisions that have to be made. Is it cross-section based? Is it point node based? So that's why I said we're going to put out a white paper, but we need help interacting with the community. This is going to take a while. It's not going to happen overnight. So I don't know FEMA's official response. They really haven't coordinated at that level yet.
There's lots of hands, Scott. You choose.
Sorry. Go ahead.
Yeah. So just a question on another level, is there a policy change or regulation change we adopt or allow for 2D and just we can get off the 1D aspects of the floodway and maybe move more toward the 2D requirements?
From a FEMA perspective, see, I can't answer that yet. We haven't really got to that point.
The folks in Pennsylvania at NTM have really had been on the forefront of getting FEMA to accept two-flow results. What is your experience, Dave, with two-flow submissions?
FEMA will accept any model that a federal highway or a federal agency will accept.
So
Well, that's from approval. They accept 2D models. It's a matter of the floodplain administrators
Yeah, well-
accepting the submittals.
getting a methodology.
Well, if you can answer that question, I think we're all good. No, quite honestly, part of the Everyday Counts program is us identifying barriers to using this technology. This is one of the major barriers.
So Scott, some of the people in the stream are state NFI, they work with their NFIP coordinators. Is that an opportunity for EDC 5 to have dialogue with that group of people?
Absolutely.
Yes.
If somebody has,
So there's the people out there
Yes.
that are involved.
we will put together peer exchanges, workshops, whatever it takes, and whoever wants to participate. We're trying to help push this forward. Absolutely. It does not. Where Flow 2D is used for floodway, they assume floodway equals floodplain. It's an easy solution in the Southwest. I don't believe, every time that I've seen a Flow 2D submitted to FEMA, that's the assumption, is that those are equal.
You
Oh, sure.
can, but
Every
determining
2D
what you-
model has that capability.
But determining which ones you block off is the question. That's the tool that we've added to do 3 different ways to determine which cells you block off to approximate that, and then you can go back and adjust those.
Take one more and then we'll,
Great.
that gentleman right back there.
Which one?
Then,
So, you talked about Army Corps, discussions. Have you had discussions about the floodway and the stuff that we've done? Because aren't they gonna have to do the same thing? They develop it, so that grass, so I didn't know.
If you talk about Hydrologic Engineering Center, yeah, they have a tool that they're trying to do something similar. I'm not sure what theirs is going to do exactly. I've been in contact with several people there in Davis, and they're going to have the same problems because the same discussion is going to come up.
And they're all attending some of these national conferences too. And I can tell you, this is just an ongoing discussion, and we keep hearing more questions rather than answers from all the agencies. So, are we done, or there's
one more from the gentleman
in the back there? Yes.
Yeah. Right.
Correct.
North Carolina is looking at funding and doing a 10-year floodway on the comparison. And the third various FEMA level is the 1-foot SPAR code in the regulations. It'll take you a decade to change.
But the question of 1 foot is, 1 foot right now means 1 foot average rise over the average cross section.
That's not how it should be raised.
But that's the way it's interpreted from the 1D model result. Yes. Yeah.
The rate still stands as 1 foot hard code.
Which would mean every node.
It just means 1 foot.
It means 1 foot, and that's it's yeah.
Thank you so much. We appreciate it.